Hello students, in this video we are going to discuss about the Bond model of semiconductor. So before going into the Bond model of semiconductor, we know that a semiconductor material can be modeled by two ways. The first one is the Bond model and the second one is the band model. Now this Bond model of the semiconductor means we want to model all the phenomena that will happen inside the semiconductor, and this Bond model is a qualitative modeling, and the band model of the semiconductor is a quantitative modeling. So what do we mean by qualitative modeling and quantitative modeling? Qualitative modeling means that we will get an idea that what is happening inside the semiconductor, but we will not gain any real picture in terms of mathematics inside the semiconductor. That is the qualitative modeling. We will only find some qualitative modeling inside the semiconductor. Now, the quantitative modeling means we'll find some equations inside the semiconductor, and that equations will describe the exact phenomena that will happen inside the semiconductor. So in this case we are going to discuss about the bond modeling, that is, it is a qualitative modeling. So in the qualitative modeling, what we'll find that some real phenomena that will happen inside the semiconductor. Okay, now in the Bond model of semiconductor, we will first consider or will assume that our semiconductor material will be intrinsic semiconductor, means it will be 100% pure semiconductor. So what do we mean by 100% pure? It means that inside the intrinsic semiconductor there will be only the semiconductor atom present. No other single atoms will present inside the semiconductor. That means, suppose if we take silicon as the semiconductor, and if it is an intrinsic material, then we can say that inside the intrinsic silicon semiconductor material there will be only silicon atom. No other atoms will be present inside the intrinsic semiconductor material. Now, since it is a qualitative aspect, and the qualitative aspect gives that what is happening inside the semiconductor, later on we will translate them into equation in the band model. The most important thing about the qualitative modeling is that it does not give you the accurate calculation, but you can have a feeling what is happening inside the semiconductor, which is also very important to understand the semiconductor material. Now let us see that what will be the outcome of this Bond model semiconductor. That means what we will get from the Bond model semiconductor. So we can write it as the outcomes of Bond model semiconductor. Now in these outcomes, so from the Bond model we can see that there are 5 outcomes from the Bond model of semiconductor. The first one is why there are electrons and holes inside the semiconductor. That means how the electrons and holes will be produced inside the semiconductor. The second one that we can know from the Bond model of semiconductor is why electrons are negatively charged and holes are positively charged. So we want to know why the electrons will be negatively charged and holes will be positively charged. And the third one is that how they are carrying current. That means how the electrons and the holes will carry the current. This is the third outcome of the Bond model of semiconductor. And the fourth one that we can know is that what will happen inside the semiconductor if we increase the temperature. So during the increment of the temperature, some phenomena will take place inside the semiconductor. We can get to know from this Bond model. The last one is there we can get a rough idea about the concentration of the electrons and holes. How much amount of electrons and hole can be produced inside the semiconductor, we can get a rough idea about that. Now let us move into the Bond model. In the Bond model, we can see that the total Bond model calculation of a semiconductor can be divided into different steps. We have to follow the steps. Step 1 is that we have to know the crystal structure of the semiconductor, and for this purpose we will take our semiconductor material as silicon. That means we want to know in the step 1 is the crystal structure of silicon. In the second step of the Bond model of semiconductor, we will discuss about the silicon crystal for T equals to 0K. That means what will happen inside the silicon crystal when the temperature of the crystal will be 0K. And in the third step, that is the last step, we will discuss what will happen inside the silicon crystal when the temperature will be raised beyond 0 Kelvin. So let us go into the step 1, that is the crystal structure of silicon. So as we know the name crystal is a special type of material, solid materials, in which there will be a regular arrangement of atoms. Regular arrangements of atoms. That means we can say that a crystal material involves the repetition of a small unit. That means a small unit is there inside the crystal material that will be repeated in the 3 direction x, y, z, and in this way the total crystal material will be fabricated. Likewise, if we take an analogy, then if we take an analogy of a brick wall, we know that the bricks is a unit, small unit, and that brick will be repeated one after another, and after sometimes we'll get the total wall structure. So in analogy we can say that the wall is a crystal and the brick of the walls is the unit structure. So every crystal will have a smallest unit that will be repeated in the 3-dimensional directions to get the total structure of the crystal. And this small unit or the smallest unit is called the unit cell of the crystal. This unit cell of the crystal will be repeated in the three-dimensional direction and will get the total crystal structure. Sometimes this unit cell, also called as the smallest repetitive structure crystal. Now, this unit cell can be of different types, but in silicon, since we are considering our semiconductor material as silicon, so in silicon the structure or the geometric structure of the unit cell is cubic. So in silicon the unit cell will be of cubic structure. Cubic structure means it will form like a cube, like a cube. So the unit cell of a silicon will look like this cube. Now there can be several unit cell structure like cubic, rhombohedral, tetragonal, and etc. But in the case of silicon, we will find that silicon will have a cubic unit cell. Now let us discuss about the unit cell of the silicon. So for unit cell of a silicon, as we have told that it will be a cubic structure. So in the diagram we can see that this is the total unit cell structure of the silicon, or we can say this is the smallest structure inside the silicon that is repeated in the three-dimensional direction, so that we get the total structure of a silicon. Now in this cubic unit cell structure of a silicon, we can see that there are 8 corner atoms. There are 8 corner atoms. So this is the first corner atom. So at every corner atom we can get this type of atoms. These are called corner atoms. This black one are the corner atoms. So from the diagram we can see there will be 8 corner atoms inside the unit cell of a silicon. So if we write that corner atoms number will be 8 atoms. This is the first atom position inside the cubic structure. Next, there will be another atom's position, that is at every face there will be one face centered atom. So this is the face centered atoms. These red ones are the face centered atoms. So as we know that in a cube there are 6 faces, so at the each face we can see that there is one face centered atom. So these are the face centered atoms. So in this way we can say there will be face centered atom number will be 6 atoms. Now there will be another 4 atoms inside the unit cell of the silicon, and the 4 atoms are at the green positions, and the green atom positions. These green atom are the 4 atoms that I am talking about. So what is the position of these green atoms? So to find the position, let us define the length of the side or the sides is of length A. Since it is a cube, we can say that all the sides will be of length A. Similarly, we can say that this length will be also A, and this A is called, in general, it is the lattice constant of the material. Now, if I am at this position A, then if I move in the x direction, let us define this is the x-axis, and let us define that this is the z-axis and this is the y-axis. I am defining three axes. So if I am situated at this A point, and if I move in the x direction by A by 4 distance, then I will be at this position. Now after that, if I move again A by 4 in the y direction, then I will be at this point, and from this point if I move in the upward z direction by A by 4, then there will be a place of atom. Similarly, if I move in the y direction, that is negative y direction, by A by 4 amount, similarly if I move in the A by 4 direction in the minus x direction, similarly if I move in the z direction, then I will get this atom. So there will be two atoms at the diagonal AB corner. Similarly, in the opposite diagonal, in the upward plane, I will get an atom at this position. So for that I have to move, if I name it as a C corner, then we have to move A by 4 in the negative y direction, A by 4 in the positive x direction, and A by 4 in the negative z direction. Then I will get this green atom. Similarly, I will get this green atom at the D corner. So these four atoms are the atoms which are placed inside the unit cube. So I can write that four atoms inside the unit cell at opposite diagonals. So we can see that there are 8 corner atoms, 6 face centered atoms, and 4 inside atoms inside a single unit cell of a silicon crystal. So from this conclusion, we can say that there will be total number of atoms present inside the unit cell of silicon will be 8 plus 6 plus 4. That means total 18 atoms. I am saying here it is the total number of atoms. I am not discussing about the effective number of atoms. That will be different. Now, from this diagram, we can see that this is a 3D figure of silicon unit cell. Now, During the explanation of silicon semiconductor material, it will be very hard to use this 3D figure of the silicon unit cell. We have to convert it into a simple diagram. Otherwise, if we use this 3D figure, then it will be very complex situation to handle the total analysis. So now we will try to make it simple. To make it simpler, we only take two important conclusions from this 3D diagram. We can see that if we consider any one of the atoms inside the unit cell, so let us consider this atom. Let us consider this black atom, and we want to find the neighboring atoms of this atom. So the first neighboring atom nearest will be this atom. This will be the neighboring atom of this black atom. Second one, this will be the second neighboring atom of the black atom, and this atom will be the third neighboring atoms of the black atom, and this pink atom will be the fourth neighboring atom. So we can say this is the fourth neighboring atom of this black atom. So in this way, if we take any one of the atoms, any one, then in every cases we can see there will be four neighboring atoms of every atoms. So we can write that the first conclusion is that each atom inside the silicon unit cell will have four neighboring atoms. Neighboring means in the nearest location. And the second conclusion that we can draw, that there will be regular arrangement of atoms inside the silicon material. Using these two conclusions, we can draw a 2D diagram, a very simple 2D diagram from the previous 3D diagram. So we have seen that every silicon atom will have four neighboring atoms. So let us take one silicon atom. So let us assume that this is a silicon atom. So this silicon atom will have four neighboring atoms. So this is the first neighboring atom. This will be the second neighboring atom. This is the third neighboring atom, and this is the fourth neighboring atom. Now, as we know that silicon has a valency of 4, it means that in the outer orbit of the silicon, if I draw the outer orbit, so this is the outer orbit of the silicon, in which there will be 4 electrons because their valency is 4. In a similar way, if I want to draw the outer orbit of the neighboring silicon atoms, so these are the outer orbit of neighboring silicon atom, then at every outer orbit we can find 4 electrons because their valency is 4. In this way, there will be 4 electrons at every outer orbits of the each silicon atoms. Now, the important case is that these silicon atoms are bonded with these 4 neighboring atoms, and the nature of bond is that they will share their own electrons with the neighboring atoms in this fashion, and they will form a bond. And these type of bonds are called covalent bonding. Covalent bonding means, in this type of bonding, sharing of electrons takes place. In this way, every atoms will enjoy total number of 8 electrons at their outermost orbit. In a similar fashion, this silicon atom will also have neighboring atoms, 4 neighboring atoms. So let us draw the neighboring atoms. So these are the 4 neighboring atoms. So similarly, these 4 neighboring atoms will also have 4 electrons at their outermost orbit. And similarly, there will be a sharing of electrons, so covalent bond will take place. So these are the covalent bond. In this way, the total structure can be drawn, and it is the 2D diagram of the previous 3D diagram structure. So we can say, or we can draw this 2D diagram in this fashion, that if I draw lines parallel to each other, suppose these are lines parallel to each other, I am making a diagram, and there is a lines also crossing perpendicular, and there will be some more lines in this way. So we can say that at every point of the cross point we will have a silicon atom. So we can say there is a silicon atom. Similarly, there will be a silicon atom. There will be a silicon atom. In this way, there will be silicon atom at every cross point of the line. This is a simple 2D diagram of a silicon atom. And the lines between the atoms means these lines are the covalent bond. So in each covalent bond, there will be 2 electrons. In this way, there will be 2 electrons in each covalent bond. So we can draw the total structure like this. So this is the simplest 2D structure of silicon that we can draw from the above or previous 3D structure. So let us discuss now about some basic parameters of the silicon material. So this type of structure we can draw from the 3D diagram. So it is a 2D diagram of silicon material. Now let us discuss about the atomic number of silicon. So what will be the atomic number? As we know that the atomic number of silicon is 14. If we see the valence electron number, then it will be 4, and the atomic concentration of the silicon atom is 5 into 10 to the power 22 atoms per centimeter cube. That means we will get 5 into 10 to the power number of atoms in one volume if the volume is 1 centimeter cube. And the lattice constant that we have discussed in the 3D structure is of the order of 5 into 43 angstrom. That is, the lattice constant of the unit cell of a silicon is 5.43 angstrom, and these bonds are the covalent bond, and these covalent bonds are produced due to sharing of electrons. So we can say there will be 2 electrons in each bond. So there must be some bonding energy of each covalent bond, and since all the bonds are same inside the silicon structure, so it has been found practically during experiment that the bond energy of a silicon will have 1.12 electron volt. So these are some practical data of silicon. Now let us see what will happen when the temperature of a silicon will be T equals to 0 K. This is the second step of the bond theory of semiconductor. So before going into that, let us see what do we mean by this bond energy. What is the physical significance of this bond energy? So if we discuss about the bond energy, then it means this amount of energy, that is bond energy, is needed if we want to break the single covalent bond. So we can write that energy needed to break a single covalent bond. So for silicon, if we apply 1.12 electron volt of energy from outside, then one of the covalent bond will be broken. That's why it is called the bond energy of a silicon. Now let us discuss in the step 2 that silicon crystal at T equals to 0 K and T greater than 0 K. That means we want to see what will happen inside the silicon material when the temperature is at 0 Kelvin. So for that case, we know that if the temperature is 0 Kelvin, then we also know that if I draw a block diagram of a silicon sample, we know that there will be atoms inside the silicon. If we draw the 2D structure, it will look like this. These are atoms, these are covalent bonding. We have already discussed about that. So this is the total 2D structure that will be present inside the silicon atom. Now, this type of 2D structure will be present inside the silicon material. Now, since the temperature is 0 Kelvin, so what will happen? So 0 Kelvin means we can say there is 0 thermal energy, and this thermal energy means this is the energy that will be present in the externally. So we can say that 0 thermal energy will be present externally outside the silicon material. So since there is no thermal energy, so we can say that there will be no agitation of the silicon atoms. That is, there will be no vibration of the atoms at 0 Kelvin. Since there is no vibration of the atoms, then what will happen? Since there is no vibration of the atoms, then we can say that there will be no breaking of bonds. Breaking of bonds means the covalent bond. So the number of breaking of bonds will be totally 0. So breaking of bonds will be equals to 0. If no bond is broken at t equals to 0 K, then there will be no generation of free electrons and holes. If there is no generation of free electrons and holes inside the silicon semiconductor at t equals to 0 K, then the current conduction capability will be totally 0. That means we can say that at t equals to 0 Kelvin, the semiconductor material or the silicon will behave as an insulator. This is very important, that at t equals to 0 Kelvin, the silicon will behave as an insulator because there will be no covalent bond breaking, and if no covalent bonds break, there will be no free electrons and holes. If no free electrons and holes, then there will be no charge carriers available to carry the currents. So we can say that the silicon will behave as an insulator at t equals to 0 Kelvin. Now, let us see what will happen if we increase the temperature beyond 0 Kelvin. So right now, we will increase the temperature beyond 0 Kelvin and we'll see what will happen inside it. Now, let us assume that we are increasing the temperature and we are increasing the temperature beyond 0 Kelvin. And we want to see what will happen inside this semiconductor material. So as we know that inside the semiconductor material, there will be so many atoms which are bonded in a covalent bonds in this fashion. There will be so many bond atoms. I am drawing only few of them. So if the temperature is now increased beyond the 0 Kelvin, so we can say that there will be finite amount of thermal energy present because the temperature is not right now 0 Kelvin, it is some value beyond the 0 Kelvin. So there will be some finite amount of thermal energy that will be present outside the semiconductor. Due to this finite thermal energy, what will happen? The atoms inside the semiconductor will start vibrating because we know that when we increase the temperature of any material, then the atoms inside the material will start vibrating. So if one of the atoms start vibrating, then all of the atom will start vibrating in this way. So if the atom starts vibrating, that's why I have written here, the atoms of the semiconductor will start vibration, or we can say that atom of the semiconductor will be in agitation. Each agitated atom right now will give rise a traveling wave, because according to the wave particle duality we know that if a matter is moving, or if it has a dynamic character like the vibration, so this atom, each agitated atom, will be vibrating. So vibrating means there will be some atomic displacement, with respect to position and time. And we know that atomic displacement with respect to position and time will produce the elastic wave. That's why I have written each agitated atoms will give rise a traveling wave. So there will be a traveling wave produced due to every vibrating atoms. Now each atoms are bonded together like a chain of atoms by the covalent bonds. So we can say that at t greater than 0k, semiconductor has agitated atoms, and these agitated atoms will give rise to traveling waves, and the atoms are displaced with respect to time and position. And this traveling wave is a wave whose atomic displacement is changing with respect to position and time. So we can say that this traveling wave is nothing but a elastic wave. So elastic wave will be created due to the atomic vibration. And we know that from the wave particle duality that every traveling wave is associated with a particle. So elastic wave is being produced due to the vibration of atoms. So according to the wave particle duality, we can say that phonon particles has been produced. Phonons are produced, and we know this, that phonon is the particle that will be associated with a elastic wave. So we can say that phonon particles has been produced right now due to the increment of temperature. This is the most important part of a semiconductor, that if we increase the temperature of a semiconductor silicon material, then due to the vibration of the atoms, phonon particles will be produced inside the semiconductor materials, and these phonon particles will now start moving inside the semiconductor. So in this way, phonon particles will be produced due to the increment of temperature. So far we have seen that phonon particles has been produced due to the temperature increment of the semiconductor silicon material. Now, after the generation of the phonon particle inside the semiconductor at higher temperature, another particle will be produced, that is the photon particle. Now let us see how these photon particles will be produced inside the semiconductor at higher temperature. So for discussing that, let us consider that this is an atom of silicon. So this is an atom of silicon. We can see that these lines are the electron cloud. We can say it as electron cloud of an atom, and this is the nucleus part of the atom. And as we know that the nucleus is positively charged and the electron cloud is the negatively charged. Now let us consider first that the atom or the silicon material is at T equals to 0 Kelvin. So when the material or silicon material is at T equals to 0 Kelvin, then the atoms are not vibrating, they are still. If the atoms are not vibrating at T equals to 0 Kelvin, then we can say that the nucleus, that is the center of the positive charge, and the electron cloud, which have negatively charged, both of them will have a charge center. That is, this total electron cloud will have a negative charge center, and nucleus will also have a positive charge center. Now, since the atom is not vibrating at T equals to 0 Kelvin, so we can say that the negative charge center of the electron cloud and the positive charge center of the nucleus will be at a same position. If I draw like this will be the negative charge center, and at this position we will get the positive charge center also, and this happens at T equals to 0. So we can say that at T equals to 0, the charge center, that is, if we say that this positive charge center will be or will coincide with negative charge center. Now I am raising the temperature beyond 0 Kelvin. So if I raise the temperature beyond 0 Kelvin, then what will happen? Now this steel atom which was not vibrating, it will start vibrating in this way. If it starts vibrating in this fashion, then the electron cloud and the nucleus will also start vibrating due to the increment of temperature. Now, since the nucleus part is a heavier material, so we know that the nucleus will have larger mass compared to electron cloud. So due to this, we can say that nucleus part will have a larger mass and the electron cloud will have a smaller mass, because electrons are of smaller masses, and in nucleus there are proton and neutron are heavier particles with respect to masses. Now this nucleus part will be of a heavier mass, and this total electron cloud is of lesser mass, and the total atom is vibrating with some frequency. So since the nucleus part will have a heavier mass, so we can say that the oscillating frequency of nucleus and the oscillating frequency of electron cloud will be different. So these two value will not be equals to each other. So the nucleus will be vibrating at different frequency, and the electron cloud will also vibrate at different frequency. So at any instant of time, we can see that the negative charge center, this one, and the positive charge center, this one, will be separated from each other because both of the electron cloud and the nucleus will vibrate at different frequency. So at any instant of time, if we see that the negative charge center and the positive charge center will be separated by some distance. Previously, both of them were coinciding at a same point because the atom was at t equals to 0k, so both of them are at same point. Now the atom is vibrating and the nucleus will have a different oscillation frequency than the electron, so at any instant there will be a gap created between the position of the positive mass center and the negative charge center. So right now we can draw this vibrating atom. This is vibrating in this fashion. So we can say there is a negative charge and there is a positive charge which is separated by some distance. And this thing, when a negative charge and a positive charge will be separated by some distance, we call it as a dipole. So a dipole has been created and this dipole is now vibrating. And we know that if a dipole vibrates, then electromagnetic wave will be generated. Electromagnetic wave will be generated, and according to the wave particle duality, we know that electromagnetic wave will be associated with photon particles. So we can say that photons particles has been generated. So in this way, if we increase the temperature of a semiconductor material, first phonon particle will be produced. Next, due to the vibration of the atoms, this photon particle will be produced from each vibrating atoms. So now we can say that we have two types of particle inside the semiconductor at temperature beyond 0 Kelvin. So if we write them, that is, the vibrating atoms is an oscillatory dipole. We have seen that. So oscillatory dipole will be radiate electromagnetic wave. We have already told that. And electromagnetic wave is nothing but photon particle stream. This is according to the wave particle duality. So according to the wave particle duality, electromagnetic wave is associated with photon particles. So we can see that at t greater than 0 Kelvin, two types of particles has been generated inside the semiconductor. The first one will be the phonons and the second one is the photons. Now these photon and phonons will now interact with each other, will interact with each other, and if the interaction energy or the total energy of the interaction is greater than the bond energy of the silicon, that is 1.12 electron volt, then it is possible that this interaction of phonon and photon will break the covalent bond. So we can write that if the interaction energy is greater than the silicon bond energy, that is 1.12 electron volt, then we can say that covalent bond will be broken. Covalent bond breaks due to this interaction. And when a covalent bond breaks, we can say that due to this phonon and photon particle interaction, one of the covalent bond will be broken. Suppose this covalent bond has been broken. So we know that in this covalent bond there were two electrons. So since covalent bond has been broken, so from this covalent bond one electron will be freed out and it will produce a free electron, and another electron will reside here in the bond with these atoms. So from one covalent bond breaking, one free electron will be produced. So we have seen that a free electron, if we write this, it will be called as free electrons, not any electrons but free electrons. So free electron will be produced from this covalent bond breaking, and in the place of the covalent free electron we can say there will be a vacancy created. This vacancy is created due to this electron has came out of the covalent bond, and this vacancy is called the hole particle. So right now we can see due to the increment of temperature, the first particle that is produced is the phonon particle, and the second particle that is produced is the photon particle. And due to the interaction of phonon and photon, two other particles has been produced. The first one is the free electrons, and the second one that is produced in the place of free electrons is the hole. So in this way these four particles are produced inside the semiconductor at T greater than 0 Kelvin. So this is how the electrons and holes are produced inside the semiconductor at T greater than 0 Kelvin. Now let us see what is these holes. What is the physical significance of this hole particle that has been produced due to the increment of temperature? So for that case we have seen that the holes that has been produced due to the breaking of bond, we can say when a covalent bond breaks, a free electron will be generated, and in the place of that electron a positive vacancy will be created, and that positive vacancy is the hole. So let us now consider that due to the increment of temperature beyond the 0 Kelvin, this bond has been broken in this way. If this bond is broken, then we can say that from this bond a free electron is created, and in the place of the free electron a vacancy is created, and this vacancy is called the hole, and this hole is a positive vacancy. Positive vacancy means that in the place of hole there is a scarcity of electron, there is a vacancy of electron, and electron is a negative charge, so there is no electron. This is a vacancy of electron, or we can say vacancy of negative charge. That's why we will say that hole is a positive vacancy. Now let us see what will happen if we give some electric potential or electric field externally at temperature greater than 0 Kelvin on a semiconductor. So let us assume that we have applied an electric field in this direction. So if we apply an electric field in this direction, it means we have applied a positive polarity at this side and negative polarity at this side. That's why the electric field is from positive direction to the negative direction. Now, due to this electric field, we can see that this free electron will feel a force in the opposite direction of the electric field, so the free electron will move in this way. And there is also some electrons in the bonds, because they are not broken right now, they are in the bonds. So at first, and these electrons which are residing inside the bonds are called the bound electrons. So one of the bound electron will jump into this hole, and this hole has been captured. So a hole will be created at this position. So hole is now shifted in this direction. Hole is now shifted in this direction. After some time, another bound electron will jump here. So hole will be shifted here. So in this way, the hole will move in the direction of the electric field. So we say that if we apply an electric field at T greater than 0 Kelvin, then the free electrons will move in the opposite direction to the applied electric field, but the holes will move in the same direction to the electric field. Actually, the holes are not moving, the bound electrons are moving. That's why we can feel that the hole is moving. Actually, there is a hole. Suppose there is a hole and there is a bound electron. So this bound electron is taking this hole, and a hole will be created at this position. So bound electron, BE means bound electron, is moving in this direction, but we can see the hole is now shifted from this position to this position. So we can say that the hole is moving in the opposite direction of the bound electron. So the movement of the hole, we can say that movement of holes is equivalent to movement of bound electrons. And bound electrons means the electrons which are inside the covalent bonding. So we can write that the free electron are moving in this direction, and the bound electron are also moving in this direction, but through the covalent bond. And the free electrons are moving here and there, they are not participating in the covalent bond, but the bound electron will move in the opposite direction of the electric field, but through the covalent bond. So since the bound electron are moving in the opposite direction to the electric field, we can say that the hole is moving in the same direction to the electric field. So in this way, we can say that movement of the hole is nothing but the movement of the bound electrons. Now, bound electrons are moving in the opposite direction to the electric field, but they are inside the bond. So we can say that the velocity of the bound electron will be smaller than the velocity of the free electrons due to the applied electric field. Very important thing is that, and this is happening due to the fact that the bound electrons are moving in the opposite direction to the electric field, but they are moving through the bonds in this way. But this free electron is not inside the bond, it is moving freely in between the atoms. So in this way we can say that the velocity of the bound electron will be smaller because they are participating in the covalent bond, and their velocity will be smaller because there will be some force moving pull back when they are moving. So we can say that the bound electron velocity will be less than the free electron velocity, and this bound electron movement or velocity is nothing but the velocity of the holes, because the movement of the holes is equivalent to the bound electron movement. So from this conclusion we can say that the holes will have a smaller velocity than the free electron. Now to capture this information inside the calculation or mathematics, we can say that these holes will have heavier mass and this free electron will have a lighter mass. That's why the free electrons are moving faster. This is the way of capturing the information, velocity information, into the mathematical analysis. We have to put this information that the hole velocity is smaller and free electron velocity is larger. So we have to put this information inside our mathematical calculation. So for that purpose we are assuming that the holes will have a heavier mass and the free electrons will have lighter mass. For this case, that's why the holes are moving very slowly and the free electrons are moving very fastly. So we can say that Mn is smaller than Mp. So Mn and Mp are called the effective mass of the hole and electron, and the effective mass of the hole is higher than the effective mass of the electron. That's why the hole is moving slowly with respect to the electron, that is the free electron. Now the important thing is that let us see how this hole movement and the free electron movement will produce the current. For that purpose, let us take a diagram like this. So from the heading we can see that I have written how the current will flow inside the semiconductor at T greater than 0 Kelvin. So from the diagram you can see these are the silicon atom and these are the electrons in the covalent bonds. So in this way there are so many electrons, atoms and covalent bonds. Now let us assume that due to the increment of the temperature T greater than 0 K, a covalent bond has been broken and a hole has been created here and a free electron has been created here. So this has been the scenario due to the temperature greater than 0 K. Now I have given a positive potential here and a negative potential here. So for that purpose there will be an electric field in this direction. So we can say that this free electron will now move in the opposite direction to the electric field. Now what about the hole? Now Similarly, this bound electron will also experience a force in the opposite direction to the electric field. That's why this bound electron will jump into this covalent hole and it will capture the hole. So right now the hole is at this position. So hole has been shifted in this direction. Similarly, let us assume that this covalent electron will now jump here. So now the hole will be shifted here. So hole has come at this position. In this way, the hole will move in this direction. So hole will move in this direction through the covalent bond. So we can say that the whole particle will move in the same direction to the electric field, but the free electron will move in the opposite direction to the electric field. So in this way, the current inside the semiconductor will flow at t greater than 0 K due to the free electron and hole. Because since the electron is flowing in this direction, so we know that there will be a current flowing due to the free electron in the opposite direction to the movement of electron. So I am writing it as I free E. So I free E is the current due to the free electron movement, and hole is moving in the direction to the electric field, and due to this whole movement we can see that I due to the hole will be produced. Now the total current I total inside the semiconductor can be written as I due to free electron plus I due to hole. This is the total current that is flowing inside the semiconductor. So this is all about the total bond modeling of semiconductor, and in this bond modeling of semiconductor we have seen how the electron and hole particle has been produced and what is the nature of their characteristics inside the semiconductor. So this is all about the energy bond modeling of semiconductors. Thank you.